let's check the attendance. Alright, let's get this started. Today I'll talk about CFD basics. So the early part of this lecture will be more conceptual explanation of what CFD is. CFD stands for Computational Fluid Dynamics. So basically what it does is we solve fluid dynamics related problems. Fluid dynamics has long history throughout the 1800s and 1900s. A lot of mathematicians have approached this nonlinear partial differential equation with tremendous amount of efforts, but they haven't come up with a single analytical generalized solution yet. So because we can't approach it analytically, we take it numerically. So we discretize the domain and we approach it in these three main branches of framework. So the first one is called FDM. It's use Taylor series to expand a variable. The second was FVM. It's finite volume method. You would integrate volumetric cell to to ensure that the conservation equation is met and there is finite element method. So what we do in computational fluid dynamics is FVM. So because of mass conservation in every Eulerian cell, we have to make sure none of the masses are disappearing out of nowhere or they appear into existence. So these are three frameworks, and what we do with CFD is to try to solve a fluid dynamics problem. One caveat here is that because computational fluid dynamics comes with tremendous resource of computers, it's really easy to fall into the trap of who has better computer per se. But these tools or these vendors are not just mere computational software. If you're using CFD tools, you have to have a firm understanding of fluid dynamics. It's not just a software A. And also another thing about this domain is the vendors are not basically unilaterally compiled per se. So it's very difficult to compare one vendor to another. For example, if you have, let's say OpenPhone is one widely used tool, and you can't really directly compare OpenPhone with ANSYS products because it depends on the situation and the problem you want to solve. So when you're asked to solve a problem, you can't just directly run into one solver and say, I'll just stick to the solver no matter what happens. What often happens is the solver you're familiar with usually come with some disadvantages and limitations. So later you have to somewhat hop on to new tool and you have to learn from the basics. So CFD works based on the principle of finite volume method. Again, it says it's integration over this Eulerian cell, but what really happens is we discretize each cell and then sum it over the entire domain so that we can replace the integration, which is computationally really hard. There are three terms in generalized Navier-Stokes equation. What's really important is the advection and diffusion term. It depends on the parameter. It can be momentum, it can be temperature. Also, if you're solving multi-species equation, it can be species, and there's generation. So if you're dealing with two-phase flow, the mass will be generated at the interface between two phases. And if you're dealing with Eulerian Lagrangian, for example, solid-liquid chemical reaction, each cell will have new chemical molecules generated because of chemical reaction on yes, in homology. So to do CFD, first of all, it's really important to define your model, and you have to understand the goal that you're setting up, because usually what happens is the goals set up the problem and the problem set up the goal, so it's sort of like reciprocal relation. So if you have a problem and if you understand what the problem really is, the solution that will come up within the problem will define the form of the solution. So it's gonna also define the methodology you can use to solve the problem. So for example, what happens is if you're dealing with a lot of turbulence models, it's really important to understand if your domain comes up with any turbulent phenomena, because if so, then you're gonna move on to turbulent models, for example, like large eddy simulation. Or if it's smaller scale, you're gonna go to like mesoscale or microscale tools. So what degree of accuracy is required is a very important question. In computational fluid dynamics, we usually say 10% is fantastic, 5% excellent, above 5% you will never see them in your life. And also another question here is, how soon do you need the results? There's one saying I get quite often is the companies usually prefer 70% accurate solution within a span of a week over 95% accuracy solution over a span of a year. So it depends on the number of mesh, it depends on the number of cells, and usually to guarantee the accuracy, there are two main approaches used. One is the mere validation with experimental results, and the other one is mesh independence. So these two are the fundamental cores of computational fluid dynamics. So when you're reading a paper, and if you're not seeing either one of them, then probably you should sort of like, have some skeptical perspective. I don't know, like with your two-sided perspective. So if you're performing a computational dynamics analysis, then make sure you have a ground truth validatable case. Otherwise, what you derive as a solution doesn't really mean much. You can't really prove that the solution is meaningful to other people. So that's one thing. And also, once you perform the sort of this numerical experiments, make sure you change the number of mesh and then perform the mesh independence analysis. So what we mean by mesh independence analysis here is when you're increasing the number of mesh, usually I don't know, at the order of 1 million to like 10 million, the results tend to converge, and then you're going to see almost identical results over a span over a certain value of mesh, let's say like 15 million mesh, and that's going to be the minimal amount of mesh you need for the numerical analysis. So and also there are simplifying assumptions. You can use symmetry and periodicity. It's really, really important. And also this is also tightly related to the CAD tools we learned in previous lectures. You have to define the domain properly, you have to understand the phenomena, and then you're going to take out the 3D model from the domain and then isolate it with proper boundary conditions. And as you can see here, I don't know why this is here, but make sure you understand if you can simplify the problem into two-dimensional axisymmetric problem. So what happens with, for example, two-phase flow is it's largely axisymmetric, so it's radially different, but axisymmetric. So you can see in the the angular direction, it has sort of same phenomena over the axis. So that's one approach you have. So these are really, really important because I've been working on computational fluid dynamics for a long time, and I just wanted to explain this once and not bother you again. And then you have to create a solid model. What you can see here is the actual solid model seems pretty unnecessarily complicated, but you can extract out the inner fluid domain, and then it can be very, very simple. You can simplify, let's say you have a heat exchanger and there's header loss and the channel loss, and depending on the formulation you want to use, you can separate them and then calculate the minor losses first and then come with channel losses, right? This applies the same way to CFD models. If you have a big CAD part and you want to analyze it part by part, then you're gonna get rid of the edges, and then if it's not really significant, because small edges require higher resolution, you can get rid of them and have some reasonable amount of mesh, and then thereby saving computational time. So this is also really, really important. And then you're going to create mesh. We usually have, compared to FEA, so finite element analysis, CFD requires a lot more cells. So in FEA, usually if you have 10,000 cells, you have like enough resolution. But usually when you're performing a CFD analysis, you're required to have, let's say, 1 million or at least 1 million, usually 10 million for steady state analysis and 15 million to, the transient analysis. So really importantly, again, it's important to know the degree of mesh resolution. And also make sure you have sufficient computer resources. PostIt has a cluster, but it's accessible to research labs, I think. So usually each lab has their own computer nodes. Our lab has one as well. And depending on the parallelism, there are two ways of CPU parallelization. One is OpenMPI and the second was OpenMP. So depending on the solver or the parallelization it requires, you can use either parallelization method that you find appropriate for the case. It's really important because people would usually assume the more cores you have, you would have better performance. But what really happens is, from my experience, after 12 cores to 24 threads, the time it takes for communication takes longer than the saving of the time. So saving of the time. So it's rather unnecessary to have more than, let's say, 24 threads for me. But it depends on the parallelism, and also these days they're applying a lot of GPU parallelism as well, so it saves a lot of your time. Another comment I want to make here is usually when you're doing your master's or PhD, I hope you assess the time it takes to perform a numerical analysis properly. Because if you can save it to like 1/3 of the time, you can basically graduate way earlier. Because this is also a numerical experiment per se, so there's always a trial and error process. You're gonna run a numerical analysis, and then 3 months later, you're gonna check the result, and you're gonna see, oh, it didn't go well, so you're gonna run it again. And then if you do it 3 times, like you basically waste a year. So it's really important to assess the time it takes really carefully, and then try with simplified models first, and then try with smaller number of mesh, and then increase the resolution and adopt more complexity to it. Yes, from my experience. And then you're gonna set up the solver. Depending on the phenomena you want to analyze, you're gonna set up different solvers. One of the solvers we use here is the Eulerian solver, but you can also use Eulerian Lagrangian solver. But also those solvers can be attached to different types of modules. So if you want to analyze like electromagnetic phenomena on top of thermofluidic phenomena, then it's going to require more computational resources. And also sometimes there comes the compatibility issue. So it's really important to understand if your vendor properly supports the compatibility. So that's really important. That's another frustration students usually often encounter. So they invest like 6 months learning one tool and then try to invest one phenomenon, and then later, like a year later, they realize there's limitation to this tool, that you can't solve this specific phenomenon, and they have to learn another tool from the beginning, and that's a tremendous waste of time. So please read the catalog properly, read them really, really carefully, understand the models they adapt, because a lot of models adapted by CFD vendors are like a simplified version of experimental results. So there's limitation to its variability and applications. So, and you're gonna compute the solution. One term you have to remember here is convergence. When you get a numerical error, we don't really say we got an error. We say we have diverging solution, meaning we don't have one set of solution. We have numerous, infinite number of solutions, or we just have like nans everywhere. So there's what we usually use is linear algebra. The solution approach we use here is usually the linear algebra related methods. So within the linear algebra framework, there's residuals for each step, and there's convergence criteria. So if the residual falls into the convergent criteria, then you can happily say the solution converged. So this is really important. I just wanted to go through this really quick, and so that everyone understands what we're doing, because it gets significantly harder than previous lecture. So after running the solver, you're gonna run what's called post-processing. So you're gonna color them, you're gonna overlay them with other geometry. So you can have a nice picture as a background. So this will also help readers to understand what you're doing, and make sure you're using proper visualization approach to display your data. One thing you can do is you can see the pressure is displayed over the surface, but also what you can do is analyzing the streamlines, and you can also plot the velocity field, or if you want, you can also display temperature field, etc. as well. But you can't put everything in one figure because they're going to overlay on top of each other. So make sure the phenomena you want to, again, make sure the solution you need and the phenomena you want to analyze. Really, really important. Yes, so we're going to use ANSYS. Postdoc gets ANSYS license as an institute, and what was it? We're using student license for our computer. So there's pre-process step, and there's solution step, and there's post-processing step. These are minor details, so you don't really need them. There are different types of mesh. These are cells, and then if the cells are all combined, we call them mesh. Usually we often use tetrahedral, so remember this shape. And we're gonna also check the grid conditions. Make sure the grid conditions cover the flow characteristics. So if there's wall behavior, you have to have a finer resolution around the wall, and depending on the turbulence model you use, if it's either K epsilon or K omega, you have to make sure you have a right wall function as well. And yeah, this is the mesh independence. If you're missing this out, please make sure you supplement this when you're writing a paper using CFD. Yep, you can see for this airfoil shape, the resolution is a lot higher around the object. It's almost black here, but near wall or boundary layer, the mesh should be denser. Anyways, that was the introduction. I hope it was not too boring, but this was one necessary step. I have to explain this. So we're gonna use ANSYS Fluent. So I'm gonna show you what we're gonna do. So we're gonna create an object using onShape, and then it's basically we're gonna draw a simple rectangle and extrude it, and then we're gonna open ANSYS Workbench and then load it. The reason I used onShape for this case was because I want to show you how this coupling of these two softwares work. Of course, you can draw the simple geometry in any other applications. Anyways, the ANSYS Workbench looks like this. We're gonna also go through this bit by bit, but if you look at the project schematic, you can add other nodes, and then you can connect the nodes. Just like if you have experience with some, let's say, or the video editing tools or Blender as well, probably you're going to be familiar with this. So there's a what was this called? There's a platform to load the STL files. You can either use Discovery Geometry or Space Plane Geometry. We're gonna use Space Plane Geometry. So it's really important to choose a language because later on you're gonna encounter an error. What I'm showing you here is, of course, you're gonna load an STL file, and when you come up with this later, you're gonna encounter this error. Yes, directory error. But the reason we're getting directory error is because our computer is not set up in English. So if you can just do this right now. Kill all the ANSYS products and then go to Workbench options and change the language from English to French first, and then French to English so that the computer can adapt to it. And then you can restart the Workbench. Yes, this is because our computer is not in English. If it was in English, you would have no problem. Anyways, you're gonna edit the mesh, and then you're gonna have this mesh dedicated for CFD Fluent, and then you're gonna choose the element size, and then make sure you can choose a face selectively, right? So if you can't choose the face selectively, then you probably have to go back to previous step. If you can choose the face selectively, then you can name them one by one. So for example, here it's gonna be create as another name selection. It's gonna be inlet, and the other side will be called outlet. And you can see the quality of mesh being 1. Yes, you should be able to see it. You're gonna create a Fluent node, and then you're gonna connect the mesh to Fluent so it can load the information that you just generated, and you're gonna update it so you can see this check mark. And then you're gonna edit the Fluent setup, and then you're gonna allow all the messages so you can see because we use this as denoted this as inlet, you can see this incoming flow to the surface, and then yeah, you can check the mesh quality again. It's going to be a perfect mesh. And then we're going to first define the model. So I just randomly chose K epsilon, but you can choose other models. And you can pretty much choose laminar as well, depending on the Reynolds number range. And you can search this online yourself. And then once we set up the model, we're going to define the fluid property and solid properties. So we're going to use air, and then we're going to have the properties constant. In some cases, you can have variable, properties, and probably you have sometimes you have to couple a user-defined function called UDFs to use this as variables. And then you're going to go to database and copy the properties of water, liquid water, and then check out the boundary conditions at the inlet and outlet. And keep in mind the Reynolds number. If the Reynolds number falls into the laminar regime, then you can choose the laminar model. Otherwise, you have to choose the turbulent model. So other than that, you're going to go to wall condition. We're using temperature boundary condition, and then if you have enough time later, you can search up what these discretization methods are. But second order upwind provides reasonable accuracy and reasonable speed. You can go to first order, and there are other methods, like plenty of methods called, for example, Runge-Kutai's one. You can find others. Anyways, you can see pressure velocity coupling is on, and then if you have time, you can check it transient. Otherwise, you're going to get the steady state solution, and then you're going to initialize and then run calculation. One important concept here is the CFL number. CFL number is defined as maximum velocity in the domain multiplied by the time step divided by spatial resolution. But if it's larger than 1, you usually have to reduce the time step, and if it's smaller than 1, you're sort of, I wouldn't say guarantee, but you're more likely to have converged solution. So other than that, you're gonna just set up the calculation activities, and then save data so that later you can see the residual running. So you can see this plot fluctuating, and then on the left, on the y-axis, you can see the scales of this residuals. What you can see here, another caveat here is if the residual is within the range of 10 to the minus 1, it hasn't converged. If it's, for example, 0.2, let's say the residual is 0.2, it hasn't converged. Even though it seems like, it might seem like it has converged, but in fact it hasn't. So no one takes this converged result. Usually, it has to go below 10 to the minus 7, and in the best case scenario, 10 to the minus 12. So once you have it, you can draw the contours, and then I was thinking of having a break, but this is not necessarily required. So once the results are prepared, you can draw contours of pressure and see velocity at the same time, and you can save and quit these. Yeah. So this is what you're gonna have. If you want to run another project, you can copy paste these nodes, and then you're gonna have them easily modifiable within new simulations. Also, another thing is if you want to keep these steps and then just you want to change the results, then you can drag and drop a result node here, and then connect this solution to this node as well. So you're gonna have two outputs from one solution node. Yep, once it's over, you're gonna go to post-processing step, and then you're gonna apply vector visualization so you can see where the velocity is pointing at, and then you can draw the contour, and later you can also plot the pressure distribution, and you can export these values. Anyways, this was the first part of the lecture. So before we move on to the second part, please follow the steps and see if you can do something interesting with the tutorial one. Don't feel pressured. This class is more of question and answers class. So if you want to understand more detailed concept of this tool, please ask me anytime. And there's no grading from this moment, right? Because these are not part of these tutorials are not part of the grading. So take it easy and do as much as you can. I'm gonna explain the second one, and then if you want to continue challenging it, you can stay. But today's tutorials don't count in the grading, so you can also leave as well. I don't want to drag everyone. But the second. Wait. Should I do this? I think I'm going to explain this very briefly, and then next week I'm going to explain more in detail. So the second tutorial will be pool boiling with ANSYS Fluent. So you're going to create a two-dimensional sketch, and then create a one solid body. And out of the solid body, you're going to take the face, so it's in 2-dimension, and then with this 2-dimension, you're going to drag it to the origin, and then use the ANSYS meshing, yes, so that it has progressively refined mesh over the surface. So you can see. On top, there's element size of 0.2 millimeters. At the bottom, it's 1 millimeter. But you see the point, right? It's 0.2 millimeter per element. Here, it's much thicker, and you can see it's progressively changing its size. So when you check the mesh quality, unlike the previous tutorial, it's not a 1. Some of them are near perfect, but some of them are very poor. You're gonna load it to Fluent, and then create a 2D space for planar analysis. And then this time you're gonna add energy equation, and then set up the turbulence model. Also include thermal effects. This time we're gonna have phase change, so we're gonna also include two fluid materials for liquid and gas, and we're gonna have copper surface at the bottom. Yep, with this with this simulation setup, you're gonna set the heat flux at the bottom to be 100 kilowatt per square meter. This falls within the range of nuclear boiling regime, and material should be copper. And the initial condition, it's all quiescent. So, what was it? Yep. With this, you can see with the heat flux provided from the lower surface, it's gonna induce nuclear boiling from the surface, and then bubbles will be formed. This calculation takes a bit, and you can later plot it based on the volume fraction and temperature at the same time, as well as the velocity field. So here, if you probe the volume fraction for a liquid, you can see most of the domain is filled with liquid, but also at the bottom you can see whole departure, which aligns with the physical phenomena. Then you're supposed to save the results. I think next week we're gonna do pool boiling, and then there's flow boiling tutorial as well. If you wanna continue challenging the first tutorial, you can stay and continue asking questions. So yeah, enjoy your lunch. Have a good day. Yeah, if you look at the screen, I can show you a good example of how these are utilized in actual research. You can see the domain is really, really fine. You can also check the number of mesh here. Any ANSYS related paper will have it, or CFD related papers will have it. So it has 10 million meshes. But what we had was like, I don't know, less than like 10,000. So, and also they set up, you can see how they set up the wall models, etc. And then later you can see their transient analysis. What was it? During this tutorial, what we used was we picked up the raw data and then made the plot within the post-processing platform, but took the results in the form of CSV, and then they plotted with another software. So this is how it usually works. I can show you other examples. So let's example. Are you a robot? Probably. Also at the same time, as you can see here, people usually have very fine mesh, and then they come up with all this interesting information. 또 클릭의 묘미가 있기 때문에 한번 말리면 진짜로 내가 왜 하고 있나 이런 생각이 들지만 배워두면 진짜 쓸데가 많습니다.
근데 결과 보니까
또 벨로시티로
대단해. 채널에는 페이크 맞나요?
아, 여기 있네요. 0.01로 들어갔네요.
인넷에 근데 인넷
인넷이네요. 죄송합니다. 예, 그렇네요.
이렇게 나오죠. 컨디션
혹시 이거 떨모번들 들어봤습니까? 혹시?
네. 그대로 따라하기는 그대로 하기는
그렇죠. 그러면 진짜 뭔 지정한 걸까요? 저 잘 모르겠네요 진짜로. 아 제가 분명히 이거 만들 때 다 해봤는데 저? 말이 안 됩니다.
벨로시티 컨트롤
이렇게 되잖아요.
근데 예를 들어 보시면은 예를 들어 이런 게 있으면은 얘를 이렇게 못 잘라요.
아, 네.
이게 안 된단 말이죠.
네.
그러니까 이렇게 이상한 모양이 나와요.
아,
근데 이런 모양이 다르잖아요.
네.
그러니까 그 완벽한 이 안 나오죠. 완벽한 거는 딱 그 격자 이렇게 딱
그 말이군요.
완전 똑같을 때.
아,
네.
이해했습니다.
에스펙트 레이쇼도 하나 중요한 요인이고요. 그리고 뭐 보시면 이제 뒤에는 나오는데 뒤에 보시면은 그 뭐야 이런 거 보면 이제 그게 다 다르잖아요, 그렇죠?
네.
그러니까 이제 이런 것들은 이제 이게 안 나오게 되는 거예요.
아.
이런 메쉬들은.
아, 이해했습니다.
네.
감사합니다.
아 왜지?
오늘 해야 되는데 원하는 게 훨씬 낫거든 말이지.
아, 다른 분들이 뭔가 이상하게 나오고 있어요.
아니요, 제가 뭔가 스텝을 하나 빼먹었어요.
아,
근데 보시면은 노슬 바운더리 컨디션 보통 쓰잖아요.
사실 이 도메인을 잘 알고 있는 게 아니라서.
들어와. 그래서 보통 이제 노슬 바운더리 쓰잖아요.
네.
제가 제 수업 들었습니까?
들었죠.
이제 전 학생입니다. 제가 2022년부터 이 수업을 하고 있어가지고
학생이신가요?
아니요, 저 대학원생입니다.
편하게 하세요. 진짜로 그러시면 진짜 편하게 하세요. 편하게 하세요.
같은 대학원생이신데.
저희 다 대학원생이에요, 진짜로. 맞다니까요, 진짜로. 아니 그 이거 보시면은 이게 진짜 이게 노슬립이 아니잖아요. 그쵸? 노슬립이 아니란 말이에요. 노슬립이면 0이었어요, 그쵸? 근데 노슬립이 아닌데 그 컨디션 어디서 주고 캡처를 안 했어요. 그래가지고 이분들이 이게 뭐냐? 왜 그 레지듀얼로 다르게 나오잖아요. 이거 지금 이렇게 나오잖아요. 이거 튀잖아요, 이렇게.
네.
벽면이 예쁘지 않아요. 근데 그게 다 잠잠하게 이렇게 되는데 왜 우리만 다르냐 했는데 알고 보니까 다 똑같이 나오고 저만 이상한 거였어가지고 아 쉽지 않았습니다 진짜. 그렇습니다. 그래서 런을 해보시면 솔직히 뿌듯해가지고 런을 해보시는 걸 한번 추천드리고요.
아, 네.
네.
제가 런을 하고
왜 왔어? 밥 먹었어?
수업 끝난 것 같아가지고
밥 뭐 먹었어?
그리고 자러 가야 돼.
감했어 진짜.
너가 최고야.
고맙다. 너가 최고다. 너도 혹시 아동학대 예방교육 듣고 싶은지 아니?
저거 왜 들어야 돼?
아니 이거 그 나 솔직히 이게 진짜 좀 억울한 게요. 저는 조교가 아닙니다. 저는 강사예요. 근데 뭐다? 다들 조교로 부른다. 그래서 저만 조교예요 여기 중에서. 이 사람들 저만 강사고 나머지 다 조교거든요. 그런데 이제 어느 순간 보니까 조교님이 되어 있었다.
그러면 강사로서 해야 되는 것도 해야 되고 조교로서 해야 되는 것도.
아 맞아. 그래서 뭐냐면 강사는 교원이잖아요.
네.
그래서 이걸 들어야 돼요. 이거 2개 더 있어요. 아직 안 들었어.
근데 왜 이렇게 고생하는 척해? 그 틀어놓고 잘 거면서.
뭔 소리야? 야 진짜로. 야 진짜 그러겠냐고 미정규 강사.
아니, 저거 딴 거 안 보고 저거만 계속 들을 거야?
연구 보안 관리 수강 신청해야지. 연구 보안 관리 해야지. 연구 데이터 관리 중요하네.
중요하지.
중요하단 말이야.
그 엑셀 같은 거 쓰는 바보 같은데.